Okay, let's just get right to it. Why is there something rather than nothing? It's pretty much the single most fundamental question we can possibly ask. Think about the exact moment of the Big Bang. The math in our standard models, it demands a perfectly balanced ledger. That intense energy of creation absolutely should have forged a 50-50 split of matter and antimatter. And, as we know, when matter and antimatter meet, they don't just hang out. They mutually annihilate in a flash of pure energy. So if the universe really started with that perfectly balanced ledger, every single particle should have been wiped out almost instantly. The entire cosmos should just be this impossibly massive, empty void of ambient radiation. The fact that you and I are literally here to even talk about this, it's a staggering mathematical anomaly.
Welcome to this explainer. Today, we're investigating the ultimate cosmic whodunit, the case of the missing antimatter. Seriously, where did half of the universe go? Somehow, some incredibly subtle early quirk of the cosmos completely eliminated the antimatter and allowed a matter-dominated universe to take over. We're going to look at the massive observational data, examine some seriously mind-bending theoretical suspects, and dig into the cutting-edge forensic evidence coming out of the world's largest physics experiments. Let's see how scientists are trying to solve the mystery of why anything exists at all. Here is our roadmap for today's cosmic detective story. We'll kick things off with Section 1, the missing antimatter mystery. Then we'll establish the rules of the game with Section 2, the Sakharov conditions. For Section 3, we're bringing in a fascinating suspect. Did black holes eat it? Next, in Section 4, we'll check out some hard experimental clues from the LHC. And finally, Section 5, solving the cosmic puzzle. All right, Section 1, the missing antimatter mystery. We really need to understand the scope of the crime scene before we start pulling in suspects. Just think about the sheer existential weight of this problem. If equal matter and antimatter annihilate each other, how do galaxies, stars, and humans exist? If the cosmic scales were perfectly balanced, we simply wouldn't be here. The ledger undeniably doesn't add up. There had to be some fundamental imbalance, what physicists call a mass asymmetry, that allowed regular matter to survive those chaotic, infinitely dense early moments of the universe. The antimatter just disappeared, leaving behind a tiny fraction of regular matter that went on to build, well, literally everything we see around us today. When we look closely at the observational evidence for large-scale annihilation of matter and antimatter, the universe is eerily quiet. I mean, if large pockets of antimatter were hiding out there in deep space, they'd constantly be bumping into rogue atoms of regular matter. At the scale of our solar system or even out in the interstellar medium, antimatter hitting the solar wind would trigger these highly specific, incredibly bright 511 kiloelectron-volt gamma ray bursts. But we've heavily scrutinized the galactic scale and massive galaxy clusters, and we simply do not detect the widespread gamma radiation signatures that would inevitably come from those annihilations. So the antimatter isn't just hiding, it's completely gone. So instead of explosive radiation, what we actually see are the quiet fingerprints of this deep asymmetry in the cosmic microwave background and primordial abundances. By mapping that oldest light in the universe, physicists can measure the exact ratio of baryons, regular matter, to photons. They do this by analyzing acoustic oscillations, which are essentially ancient sound waves frozen right into the temperature fluctuations of the early universe. By measuring the precise spacing and amplitude of these waves, cosmologists can effectively count the density of surviving regular matter against the sheer volume of light left over from that great annihilation. It's like finding a cosmic fingerprint, proving mathematically that this life-giving asymmetry is completely hardwired into the cosmos. Moving right along to Section 2, the Sakharov conditions. Before we start pointing fingers, we have to lay down the strict physical rules that allowed this imbalance to happen in the first place. Back in 1967, the brilliant physicist Andrei Sakharov proposed 3 specific conditions that must be met to get from a perfectly balanced Big Bang to an unbalanced, matter-dominated universe. First up, baryon number violation. There has to be some physical process that fundamentally alters the net number of baryons, basically allowing matter to outpace antimatter. Second, C and CP violation. This means the fundamental laws of physics must carry an inherent bias, treating matter and antimatter just slightly differently. And third, a loss of thermal equilibrium. This one is absolutely crucial. The universe had to undergo rapid expansion and cooling, acting like a one-way street. Because it cooled so violently, the particles lost the thermal energy required to reverse their interactions. That permanently froze the imbalance into place. Any theory trying to solve our mystery has to obey these 3 strict laws. Now, for Section 3, did black holes eat it? Let's bring in our first really compelling theoretical suspect. Theoretical physicist Nikodym Poplavsky has put forward this deeply fascinating idea involving primordial black holes. Now, unlike the black holes we normally talk about, the ones born from dying stars, these hypothetical seeds would have formed from extreme, high-density fluctuations fractions of a second right after the Big Bang. You have to imagine the early universe not as this empty vacuum, but as a blistering, chaotic subatomic feeding frenzy, where microscopic regions of space just collapse directly into black holes. The core of this theory relies on a vital mass difference during that blistering epoch. Poplavsky theorizes that in those extreme conditions, antimatter coupled slightly differently to expanding scalar fields. This subtle interaction would have made antimatter particles heavier and therefore far more sluggish than their regular matter counterparts. Because the antimatter was heavier and slower, it was captured by black holes at much larger rates. It literally couldn't outrun the immense gravitational pull of those primordial black holes. The regular matter particles? They were lighter, much faster, and basically zipped away to construct our universe. So the missing antimatter didn't vanish. It was just swept up and eaten by microscopic black holes. And what elevates this from a neat idea to a truly breathtaking theory is how it simultaneously targets another major astrophysical crisis. Could this antimatter binge eating explain the impossible size of early supermassive black holes observed by the James Webb Space Telescope? JWST recently sent cosmologists into a tailspin by spotting supermassive black holes just 500 million years after the Big Bang. Under standard models, they shouldn't have had nearly enough time to gorge themselves to that size. But if Poplavsky is right, and those early primordial black holes spent the dawn of time binge-eating incredibly heavy, slow-moving antimatter, well, that enormous head start in mass brilliantly explains how they ballooned into those supermassive giants. It is just the ultimate double solution. All right, that brings us to Section 4, Clues from the LHC. Let's shift gears from the macroscale astrophysics of black holes down to the microscale experimental particle physics happening deep underground at CERN. Before we dive into the data, let's quickly refresh our understanding of CP violation, which, remember, was the second of those Sakharov conditions. Modern physics relies heavily on CPT symmetry, the idea that charge, parity, and time operate in perfect balance. CP violation is when particles and their antimatter counterparts decay differently, breaking that perfect symmetry between them. Finding a flaw in this mirror implies a fundamental bias in the universe's hardwiring. The laws of nature actively prefer one over the other. Our standard model predicts a tiny sliver of the CP violation, but honestly, nowhere near enough to explain the survival of all the matter in our cosmos. Physicists definitely need to find more of it. And finding that hidden violation is exactly what the LHCb collaboration at the Large Hadron Collider has been obsessively hunting for. These researchers literally counted decays of bottom lambda baryons and beauty hadrons to find matter-antimatter differences. Why these specific particles? Because they're incredibly massive and highly unstable. Standard model physics says if cracks in perfect symmetry are going to appear, they're most likely to show up in the complex decay paths of these heavy fleeting particles. So, by sifting through the colossal wreckage of millions of proton-proton collisions, they meticulously counted how the regular matter versions decayed and compared it directly to the decay paths of their antimatter twins. The results? They yielded a difference with a significance of 3.2 standard deviations. Now, in the rigid, uncompromising world of particle physics, 3.2 sigma means there is roughly a 1 in 1,000 chance that this data is just a statistical fluke. Sure, that falls a bit short of the legendary 5 sigma gold standard you need to declare a formal scientific discovery, but it is an absolutely massive clue. Observing this level of CP violation specifically in baryons, those heavy 3-quark particles that make up the protons and neutrons inside you and me, has historically been notoriously difficult. This 3.2 figure represents incredibly solid experimental evidence that's actively chipping away at the supposed perfect symmetry of our universe. Finally, let's look ahead to Section 5, Solving the Cosmic Puzzle. Where exactly does this investigation go from here? We are standing right on the precipice of a new era in physics. To confirm those tantalizing LHCb findings, scientists are looking forward to future clues from the high-luminosity LHC upgrade. That's going to deliver significantly more collision volume, giving us the raw statistical power needed to finally hit that elusive 5 sigma mark. Meanwhile, testing Poplavsky's theory about primordial black holes will rely on next-generation gravitational wave observatories. They're actively hunting for the specific high-frequency signatures of tiny, ancient black holes merging in the deep cosmos. Couple that with deep underground neutrino experiments probing the high-density behavior of the early universe, and the net is really closing in. So, what future cosmic clue will finally crack the case of why we exist at all? Whether the ultimate answer is hiding in the microscopic wreckage of particle collisions deep under the Swiss-French border or echoing in the gravitational ripples from the absolute dawn of time, this investigation is profoundly personal. The missing antimatter isn't just some abstract physics problem. That very imbalance is the entire reason we even possess the capacity to ask the question in the first place. We are literally the conscious, surviving remnants of the greatest disappearing act in the history of the cosmos. Thanks for joining me for this explainer. Keep your curiosity sharp and never stop investigating the universe around you.